So now let's go through some examples of how you use a cache. So we're going to take a look at where data can go in a cache. And we're going to start out with a fully associative cache. So here's our fully associative cache. We've got tags and we've got data. Let's take a look at this address here, address 180, and here it is in binary. Now you'll notice the last two zeros here, these are the byte offset within the word. So I'm assuming we have one word per line in our cache, and since we need to have word-aligned accesses and MIPS, these are always going to be 00. So where can this address go in the cache? Well, this address can go anywhere in the cache. The cache is fully associative, and fully associative means we can put any data anywhere we want. So I'm going to go ahead and put this here. It could be at any other place, but I'm just going to put it here for now, and here's the tag. So we've got the full tag which tells us what data is there. How about this other address, 244? Where can it go in the cache? Well, since it's a fully associative cache, it can also go anywhere, so I'll go ahead and throw it in here. Now, when we talk about a fully associative cache, we can put the data anywhere. That means we don't treat any of the address bits as index bits. We're not indexing into the cache. We're not telling it where to put the data based on the address. It's because it's fully associative, we can put it anywhere. It also means that when we go to look in the cache, we have to look everywhere. Let's compare this to a direct map cache. So a direct map cache also has a tag and data, but it has this indexing scheme. Every address can only go into one place, and we determine what that place is by the index into the cache. So here we have an 8-entry direct map cache, which means the entries are going to be mod 8 with the address. So again, let's take a look at an address. Here's address 180. Where is this going to map into the cache? Well, address 180 can only map into one place in the cache. So we use these 3 bits here to determine what the index is, and if you look at these 3 bits, well, that's going to map down here to the 5th entry. So it's an 8-entry direct map cache. We need 3 bits to index into it. We're not going to use the first 2 bits because they're the byte offset, so the next 3 bits we're going to use to determine the location. So in this case, this one has to go into the 5th entry here, because the index from the address says it has to go there. So how about this other address, 244? Where's it going to go into the cache? Well, to figure that out, we look at the index bits for this one too, and the index bits match. So for 180 and 244, they're the same index bits. That means both of these have to go to the same entry in the cache. So our cache can't hold both at the same time. If we want to put address 244 into here, we're going to have to get rid of the other address and put it in. Now when we go ahead and put it in here, you can see we have our tag. And our tag's much smaller here. The tag is smaller than it was up here in the fully associative cache because part of our address tells us where we are. If we're looking at address at entry 5 into the tag cache here, that's because our address has already told us to look here. So we don't need to store those bits again in here. So in this case, both addresses 180 and 244 map to the same index, so we can only store one in the direct map cache. Now the compromise between the two of these is a set associative cache. So a set associative cache has some flexibility that you can put any data you want anywhere in, you can put data anywhere you want within a set, but each address only maps to one set. So let's take a look at what we have here. Here's address 180. Where does that map into the set associative cache? Well, address 180, if we look at it, is going to map into set 1 here. And we can see that because we have a 4-set set associative cache, so we need to do 2 bits to determine which set we're in. So we have 4 sets here, we have 2 bits, we can tell that it's going to put it in here, we can put it anywhere we want within this set. So I'm going to go ahead and put it in the first one here. Now how about this other address, 244? Well, address 244 is going to map to the same set, but unlike the direct map cache, we can put it anywhere we want in this set. So I don't have to kick out this data to put it in, I can put it in here as well. So both of these addresses map to the same set, but because I have the flexibility within the set, I can keep both of them there. And you'll notice that we have 4 tag bits here in our set associative cache because we only have 2 index bits told to us by the set. So if we're looking in this set, we don't need the index bits stored in the tag because when we're looking in the set, we already know the index bits in order to look in the set. We just need the rest of the bits for the tag. So to summarize what we had here, we've got fully associative caches, which are very flexible, and we've got direct map caches, which are very inflexible. Every address has to map to one of these entries, and we use bits from the address in order to choose the index. In the middle, we have the set associative cache, which has some flexibility within each set, but we also have some limited flexibility in that each address can only go into one set. When we looked at how the addresses were interpreted, we saw the fully associative one doesn't use any of the bits for the index because things can go anywhere. So you can put the data wherever you want. This also means it has a larger tag because even though I'm looking in this location here, I have to have the full tag to know what the data is because there's no index that tells me something about this location. The direct map cache is different. So here we have an index bits directly in our address, or sorry, we use some of the bits from our address to index into the cache. And this tells us this address can only go in one place. And in the case we had here, both of these go to the same place in the cache, so we could only have one at a given time. But we need very many fewer tag bits because when we're looking at this location in the cache, we know the index has to be this value. We can put those together to get the full address. And the set associative ones in between. Here we have fewer index bits than we had over here, which means we have more flexibility, but we have more tag bits because we have more flexibility, and where we're looking in the cache tells us less about the address. So in this case, we could put both of these values in the same set, and they didn't conflict with each other because we had flexibility within the set. So we use some of the address bits to know where the address has to go if it has to go somewhere. So in the case of the fully associative cache, it doesn't have to go anywhere, so we don't use any of the bits for the index. We don't need the bits from the index and the tag because they're implicit in the location. If I'm looking at this location here, the third entry in the direct map cache, I don't need to store the 011 from the index and the tag because I know the 011, that's how I looked at this location in the cache. Same thing over here in the set associative. If I'm looking in this set here, well, I already know that the set bits are 1, 0. I don't need to store those in the tag. And in general, the more flexibility we have, the more tags we need and the more searching. So for the fully associative cache here, we need a lot more tags because where we were in the cache didn't help us. We had to search everywhere. Whereas over in the direct map, we needed fewer tag bits because where we were in the cache told us something about the address, and so we didn't have to do as much searching.